as you can see that I have chosen to adapt the Fritz-Haber solution to haircuts, as pointed out by David's original presentation. Now, the two previous speakers have chosen more imaginative. Not gone along simple. However, let's proceed on to the more important matters. I want to talk about carbon 13 NMR, graphite, charcoal, and coronene, small molecules. And I assert that this is basic data for NMR studies of catalyst coating. Now, how is graphite, at least the graphite that we use for studies of graphite and percolation compounds, and that nature, how is that made? Well, it's made by pyrolysis of small molecules. How is charcoal made? It's made by the pyrolysis of natural products. Of course, coke, as it occurs on catalysts, is also a pyrolytic product. So we're not really too far afield when we work with these other substances and looking at coke. Okay, now let us do the C13 NMR spectrum, measure the C13 NMR spectrum of graphite. Now we are able to obtain from union carbide a sample called highly ordered pyrolytic graphite. This is again made by the pyrolysis of methane on an iron surface and it's then pressed, and it's well ordered with the C-axis of the graphite. In other words, the graphite consists of planes. These planes are highly parallel to one another over the large crystallite that we use. And but it's really a polycrystalline mass with all these axes parallel. All these planes parallel. But there is disorder in the plane as you go from one crystallite to another. So we're concerned then with in this experiment with the orientation of the plane normals with respect to our magnetic field. This is essentially a single crystal experiment. And we can measure the chemical shift as a function of this angle. You'll notice that there is a dependence on angle. Now, why is that? Well, it's a fundamental property of the NMR chemical shift tensor that depends on the way you hold the magnetic model in the magnetic field. The chemical shift is due to shielding by the electrons. Naturally, it must depend on how the electron arrangement is placed in the field. So there is this dependence on the angle. For those of you who may have done nuclear magnetic resonance spectroscopy in liquids, and even those who have done magic angle spinning in solids will say, gee, these lines are horribly broad. And if you do a spectrum for a well-crystallized solid, you expect these lines to be very sharp. So one of the things we're going to inquire into is why these lines should be as broad as they are. But nevertheless, they do show a dependence on the orientation. So this is then how the chemical shift looks for the best graphite that we have been able to get. So we're trying to understand why those lines should be the way they are. Well, we're going to take a long, roundabout way to do this. Here we have the structure of the graphite, and as you can see here that these layers are not stacked hexagon over hexagon. Each alternate layer is shifted. So this layer and this layer are hexagon over hexagon. So this layer puts one of the carbons over the hexagon below. So we can spread these layers of graphite apart by putting intercalants in the layers of graphite. For instance, we can react ASF5, take 2 electrons from it and put them on take 2 electrons from the carbon and deposit 2 positive charges on the graphite, make some ASF6 and ASF3. These are all between the layers of the graphite, all of these different chemical species. And one of the things you want to look at is finding equilibrium constant for this reaction, but that's not the topic today. And we can also use other reactions to put, say, if you want to put just ASF6 and not have this mixture of things in there, we can use this reagent. React with graphite, and we put ASF6 in there. The NO2 goes off as gas, and unfortunately, though, a little bit of nitromethane goes into these graphite layers as well. So, what happens when I do this intercalation? Well, okay, I should mention before I go on to that a strange phenomenon occurs when you do intercalation in graphite that you can well, this is a reaction with a metal in which you generate positive ions instead of negative ions. But anyway, the thing I wish to refer to is this phenomenon of staging. In other words, you're able to make compounds in which you have every other layer, so to speak, is intercalant. You have graphite, intercalant, graphite, intercalant. And you can make what's called a second stage compound. You have 2 graphite layers between every layer of intercalant. 3, and 4, and 5, and so on. And the interesting thing is that this does actually occur. In other words, you very rarely have a mixture of 3 and 5, say. That just doesn't occur. When you have the right composition, there are always 3 layers between layers of intercalant. And it's interesting that for those who are interested in catalysis, in the symposium, that these are reputed to be catalysts in themselves. And so we have some contribution to these. Okay, you'll notice that these lines get very narrow now. This is the same thing as we showed on the first slide. We have chemical spectrum as a function of the orientation of the c-axis, the plane normal with respect to the magnetic field. And you can see that the lines have become much sharper. And the thing is, why is this? Why would pure graphite so messy and the lines here are much sharper? Well, I believe it's because in the graphite there is poor stacking of the plane. When we put in the intercalant, we actually free the planes from the influence of the neighbors, and in this case, we actually go to a disordered arrangement of planes with respect to one another. And this is able to give us very sharp spectra. One of the byproducts of this is the spectra are so sharp that we can use NMR chemical dipolar coupling between neighboring carbons. In other words, carbons are only about 1% abundant. Suppose we concentrate on the central carbon. That means that at the first neighbor position, the odds are that 1 in 100 of this at this neighboring position will be another carbon 13. The carbon is only 1% abundant. So that means the probability that one of these 3 neighbors will be another carbon 13 is about 3%. And likewise, we have 6 second nearest neighbors and 6 3 third nearest neighbors. And because the nuclei are magnets, they exert a small magnetic field at the side of one at the side of the other. And this gives rise to a splitting in the spectrum. So here we have the spectrum of most of the C13 nuclei that don't have any near neighbor carbon-13. And here we have spectra due to the first nearest neighbor, second nearest neighbor, and third nearest neighbor, and so on. And we do that. This spectrum was taken with the magnetic field normal to the plane of graphite, so that we can, all of these will have exactly the same splitting. We have chosen other angles that measure in standard. But this allows us, because we know the way this field varies as a function of distance, to actually measure the size of the graphite crystal. So that's one of the things we can do with graphite interpolation. And another, which is really going far afield, but nevertheless, when we make graphite fibers, which are made from pyrolysis of pitch, often they can be viewed as certain cigar shapes, where you take these planes of graphite and you wrap them around a central fiber axis. This means that the C-axis, the normal to the plane, will be distributed, will always be perpendicular to this fiber axis, but it will be equally distributed over all angles in the plane normal to the fiber axis. And this gives you a certain kind of spectrum, which is one of the things I want to get into. But anyway, in order to sharpen this up, we had to interpolate it with ASF5 to get the nice sharp spectra. Because if I use just raw fibers, I wouldn't have, I get a very broad spectrum because of the crystalline perfection. But as we pointed out, the ASF5 sort of lubricates the system and makes the spectra very sharp. And this spectrum that we see here is called a two-dimensional anisotropy pattern. It's not a pure two-dimensional pattern because then both of these beats would have been the same. So from this I can actually calculate the perfection of the alignment of the graphite fibers, and they are within 85% of the 85% of the carbon planes in the graphite are just as described in this model. The other 15% are bent. Okay, well, enough for fibers. I still wanted to get to the model as to why are those lines so broad. Well, here we have another interpolation system in which the two extremities are very narrow. Somehow the nitromethane wetting the sample has gotten in the way, and we just have to get that part out. So anyway, you can see that at this orientation, the magnetic field parallel to C, and here for perpendicular. This is anyway. You can see that the two extreme orientations are very narrow. We have a broad line in the middle, and this is because we have a distribution of orientation to the plane. So this is one kind of imperfection you can have, a distribution of orientation. And here's another interesting thing. We take a stage 2 compound in which we have 2 carbon layers between every layer of ASF5. Then we get a doublet of this orientation. That means there are 2 different kinds of carbon atoms in that specimen. What 2 kinds of carbon atoms can there be? Well, the only way you can find two kinds of carbon atoms in the absence of some very specific chemical interaction of the ASF5 with the graphite is as follows. Divide the carbon atoms up into two kinds. Well, here we have this part of the graphite net, and we just arbitrarily label every, in a symmetric way, half the carbon atoms with green dots. Okay, now let's put the next layer, the way graphite is usually stacked, with AB stacking, on top of that one. And you can see that, yes, there are two kinds of carbon atoms. You have two layers stacked on top of one another. There are those that are above rings, plain below. There are those that are above carbon, plain below. So this is clearly the only way we can get two kinds of carbon atoms. And this shows that stacking of the planes actually contributes to the broadening of the line. So how then do I explain these broad lines? Well, I assert that this graphite is really very poorly crystallized, and we don't have just AB stacking, we have ABC stacking, which is another, and these can be random runs of these in the crystal. So that even though graphite is a crystalline material, it is not perfectly crystalline, and that's why we get those broad lines. So what does this say then as far as coke is concerned? Well, if we want to model a coke by graphite, we can say that graphite has a rich chemistry, and the chemistry affects the C13 spectra. And if that's the way it is with a crystalline compound, how is it going to be with coke, which is even less well organized? So that coke within limits might look like graphite, but it will have problems with it. Well, let's go on to a charcoal absorbent. And I'm concerned with charcoal absorbents because of they're used by the Navy in atmospheric cleanup filters. But there is a model of graphite, of charcoal, which says that you just have graphite planes in the form of ribbons that wind their way through space, touching here and there. They have pores in the middle, or here and there. And they also have, they're imperfectly formed so that you not only have hexagons, but you have occasional 5-membered and 7-membered rings. Well, this is a model of charcoal. How can we use, and one might think how is, might even model coke. So what does charcoal do? It has pores, it has surfaces, and it has edges. So graphite regions are only of limited size. So let's do NMR spectrum of charcoal. Well, there it is. This is a powder of charcoal. You could do a magic angle spinning spectrum and narrow it somewhat, and we have done some of that. But I'm concerned with the shape of this powder in isotopy gas. And this end of the spectrum corresponds to the magnetic field lying in the plane of the graphite, and there are a lot more, there's a greater probability of having that orientation than having it at unique orientation with the magnetic field parallel to the C-axis, the normal plane. So that's the kind of spectrum called an axial powder pattern that you expect. Now, here's an axial powder pattern for a more well-defined system. You can see the infinity here on this side, which is the sharp shoulder on this. This is for actually for benzene absorbed on the surface of silica gel, a C13 NMR spectrum, which we obtained 6 years ago. And it does have this actual pattern with the infinity on one side and the step on the other. So that's what charcoal would look like if it were perfect. You can compare the difference. So that you know that charcoal is somehow much more disorganized. Now, why would benzene have the actual symmetric powder pattern? Well, it turns out that this is completely accidental. This happens because the benzene molecule is rotating about its six-fold axis. And this gives the appearance of an axial symmetry. If you cool the benzene down to, say, liquid helium temperatures, you get what's called a completely anisotropic pattern. So, rotating benzene looks like this. When you cool it down, it looks like this. And it no longer has the appearance of axial symmetry. In other words, a benzene molecule, a carbon atom in a benzene molecule does not have threefold symmetry, so it gives you this type of anisotropic pattern. And I'm going to assert that this is what you expect for the edge of a charcoal ribbon. And I'm going to assert that this is what you expect for the interior of a charcoal ribbon on the basis of our graphite study. In other words, this is the calculated pattern based on graphite. And if you have, say, a third of the carbon atoms at the edge, and the rest, most of the rest in the interior, you have some sum of these kinds of spectra. And you might even have a little bit of aliphatic stuff that you have to add in, and you get some patterns that look like this. And then when you put in an appropriate broadening by, you can probably pick the spectrum that we have for charcoal, and we tried that on another spectrum. And so, if we said the carbons were interior only, or if we had 62% interior, 34% edge, and 4% aliphatic, they both of these models fit the data equally well. But we hope to get better spectra and see if we can do a better job. So we're getting to, proves to be a little difficult here. But anyway, let's consider what people who use X-rays on charcoal have developed. Well, they assert, Connerton and Antonio, looking at a certain charcoal, have said that that ribbons in which you have, we call these B ribbons, because you have the B axis of the graphite sheet parallel to the ribbon direction. These are not allowed by the X-ray studies. We can only have these, the A axis goes that way and B goes this way. Not have the B going this way. So we know that the ribbons must look like this. And we can see that they must have these dimensions. And you can see then that the model we adopted we should expect that about 2/3 interior, about one-third exterior, if we had models of those dimensions. Well, I'm going on to another model of charcoal system, and I'm really getting basic here, I guess. I could try coronene and say this is a fragment of charcoal. this is about the smallest piece of charcoal that you can really have. If I'm going to say that the outside of the charcoal is 2 atoms thick, in other words, these belong to the outside of the charcoal ribbon, then in this model, coronene, I have an inside and an outside. So this is the model. This is a nice piece of charcoal that I'm going to look at the carbon-13 NMR spectrometer. And lo and behold, when I do it at room temperature, gee whiz, I get these axial powder patterns. That means the molecule is rotating rapidly at room temperature, and I'm not getting the effect I wanted. So I have to go to low temperatures and look at the spectrum. Okay. So what am I expecting? I guess to use I'm expecting that the outside edge carbon atom will look like this, and the interior will look like this. In other words, if I see this sharp axial pattern, then I know I have some interior carbons. And if I see this broad pattern, then I know they have some edge carbons. And I want to count the edge and count the interior one. And so here we have then the spectrum at low temperatures where we stop the rotation. And you can see then that there's a sharp edge on this side. There also is the mark of the full anisotropy pattern. And we can use different cross-polarization times to select those carbons that are near protons, because we're doing something called cross-polarization as part of this C13 experiment. And if we cross-polarize for a very short time, we only see the ones that are near the protons, and you can see that they have the full anisotropy pattern. We get the whole spectrum, those that are near and far from the proton, and we get this axial peak here. So we can subtract this one from this, and we get a very crude but indicative axial spectrum, which is about a fourth of the total. So we've modeled charcoal with the small molecule coronene, and we've shown that the edge is about 2 atoms thick, and we should be able to use C13 NMR spectroscopy to measure the dimensions of ribbons in charcoal, and by extension, perhaps do the same thing for coke on patterns. Well, I've told you about graphite, charcoal, and coronene. I've gotten the basic C13 NMR parameters, chemical shift and isotropy patterns, principal values, and the principal directions. And one should be able to use these to studies of coking patterns. So we have time for one question for this thing.
You did see a dipole coming along the stack because of that.
Well, yeah, the dipole interaction, all the angles are distributed there. There are no unique angles. It's only the ones that are in the plane that have unique theta and the 3 cosine squared theta minus